Hello, 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 and welcome back for another video. Today we're going to be talking about communication circuits, and I am a little bit curious about how much of this you have actually learned in your evening course that you had, because I know many of you are in the gas and oil field, and you are not taking the broad-based electronics program, and therefore a lot of this material will be new for you. So, first thing is, we only have a couple more videos to go, 2 or 3. And then I'll be passing out your practice test to give you an idea of how well you're going to do on the CET. I would like those of you who have not contacted me to please let me know if you're thinking or not thinking about taking the CET exam. Those of you that have followed my instructions and have emailed me, I greatly appreciate it. Those of you that have not, will you please email me and let me know your intentions. If you are not taking the CET exam after this next quiz, there's a very good chance you won't have to do any more work and you can pass the class. So I don't want to make you doing work that you don't have to do. You don't have to take the CET test to pass the class. So let me know what's going on and we'll go from there. So, why don't we start off? With no further ado, let's get it on and start covering those activity sheets. Hopefully you've printed them out and you're ready to fly. Okay, your first activity is about decibels. Did you learn anything about decibels in your 5th quarter communications class? If you did not, you got shortchanged. I know that some of you had an adjunct teacher for 5th quarter in your communications class. I was a little bit concerned about what was going on in there, but let's go ahead and talk about it. So, why do electrical engineers and technicians use decibels for measurements? I'm sure we've all heard of the phrase dB or decibels. Well, the reason why we like to use decibels as a unit is because decibels makes it possible to use extremely large numbers and extremely small numbers together. You know, for example, we might be talking about the number of seconds in 10 years. That's quite a large amount of seconds. Or we might be talking about the number of seconds, a picosecond, which is a very, very tiny amount of time. But decibels makes it easy to use really in big and really small numbers. It's a way to allow the human mind to comprehend numbers in a fashion without dealing with the large distances between. You know, look at the national debt. What is it right now? $20 million. Obama said he was going to reduce it when it was only $10 million when he came into office 8 years ago. Well, forget about that. But if you compare that $10 trillion to 1 cent, it wouldn't really make any difference, would it? So another reason why we like to use decibels is that decibels is a way to compare voltage, power, and current with the same unit. So you can actually convert voltage, current, and power into the unit decibels and do a one-on-one comparison. For example, right now, if you haven't had decibels, you can't really compare 100 watts to 10 volts or something like that. But the decibel unit makes it easy to compare two items one-on-one. It's like saying, well, you can't compare oranges to apples, but when you use decibels, you can. Now, what are the most commonly used decibel numbers? Well, the two commonly used decibel numbers are 3 and 6 dB. Those are the most common, and they have a very, very important meaning to them. And to begin with, anytime you have a positive number of decibels, for example, positive 3 decibels, 3 dB, usually it's a small d and a capital B, that means it's going to be, increasing the voltage, power, or current will always be a positive value, as in number 3 here. So if you have a positive 3 dB, you know you're increasing the number of volts, power, or current. Likewise, if I have a negative number of decibels, for example, negative 6 dB, we're just focusing in on the sign in front. If we have a negative 6 dB, that means we're going to have a smaller number of voltage, power, or current. So the key to using decibels is the 0 dB reference. Anything above 0 dB will be a positive, which means it's an increase. Anything below 0 dB, a negative number, will be a decrease. Now you have to be careful here because the positive number in front of this, the positive sign in front of this number right here, that actually may be omitted, so you might just have 3 dB, and it's understood to be a positive 3 or 6 dB. It's understood to be positive. But if you hear the word an increase in dB, that always means a positive. But down here, when you're looking at this one, it has a negative sign in front of that, and a negative sign in front of the number always means it's a decrease in the value. But quite often, they'll leave that negative sign off and they'll say you have a loss of 6 decibels. Well, when you hear the word loss, that automatically means it was an increase. I mean a decrease in the number. So that's what we have to be careful of. If you hear the word increase, it's going to be a positive value. If you hear the word decrease, it'll be a negative number. So watch for that, because sometimes on the CET questions, they'll say, I have a loss of 6 dB. Well, that negative sign is understood to be there when you hear the word loss. Okay, the most important numbers for decibels would be a 3 and a 6. Let's tell you why right now for number 5 on this activity sheet. A positive 3 decibels here for number 5 always means you're going to double the power. So if I was to start off with 1 watt and I had a positive 3 decibel increase, that means I would have 2 watts. Or if I had 2 watts and I had a positive 3 dB increase, that means it would be 4 watts. So anytime you have the number 3, that means that you're going to have a doubling of the power. Not voltage now, we're talking about power. So a positive 3 decibel number means I'm going to double the power, no matter what the original power was. I can have 2 megawatts, but if I increase 3 dB, I'm going to have 4 megawatts. I'm multiplying it by 2. Now, likewise here, a negative 3 dB always means I'm going to decrease by 3 dB, or I'm going to cut the power in half. So a negative 3 dB means I'm going to cut the power in half. So if I have 2 megawatts and I go down 3 decibels, I will have 1 megawatt left. If I have 1 watt and I go down 3 decibels, a loss of 3 dB, I'm going to cut that power in half. That would be a half of a watt. If I have 1 milliwatt, half of that would be 500 microwatts. So, very important number, 3. A positive 3 always means a doubling of the power. Negative 3 always means a halving of the power. So whatever power they give you, if you increase by 3 dB, you're doubling it. If you decrease by 3 dB, you're cutting it in half. Now, another important number is 6 decibels. A positive 6 decibels means I'm going to double the voltage. A positive 3 means I'm doubling the power. But a positive 6 decibels means I'm doubling the voltage. So if I start off with 10 volts, and it says I have to increase the signal by 6 dB, I'm going to go from 10 to 20 volts. That's all that it means. Now here's a really interesting aspect about this. 6 decibels always has a meaning for power. That's what we're getting at here for number 8. If the voltage doubles, I'm going to have 6 decibels. So the voltage doubles. That's a positive 6 dB, no matter what it was. But to go up to 6 dB, I have to go up 3 dB 2 times. So I go up 3 dB once. That brings me from 0 to 3 dB. And then I go up 3 dB again. That goes from 3 dB to 6 dB. So what did I do to the power? Well, any time I double the voltage, I'm going to go up 6 decibels, I also have to increase the power twice. So let's just say I start off with 1 volt for a given load. I have 1 watt. and I'm using 1 volt to generate that 1 watt. Well, if I go up to 2 volts, how many dB have I gone up? Well, that would be 6. But for the power, if I double the voltage, I'm not going to double the power. I'm going to quadruple it. Here's why. I go from 3 dB up from 0 to 3. That's from 1 watt to 2 watts. And then I go up 3 dB more, which for a total of 6, that's 4 watts. So any time I increase by 6 decibels, I'm going to increase the voltage by a factor of 2. But because the power is doubled twice, 3 dB and 3 dB, to give me 6, I'm going to quadruple the voltage. It's really important. So that's what we're getting at right here. Right here. We're getting at this thing right here. If the voltage doubles, you've increased 6 dB, and this is 3 dB twice, so the power will quadruple. Now, it works the other way, too. You know, I told you before that if you go down 3 dB, you're actually going to cut the power in half. But to go down 6 dB means you're going to cut the voltage in half. So anytime I go down 6 decibels, the voltage is divided by 2. Okay, give you an example. 100 volts minus 6 dB would be 50. Minus 6 dB more would be 25. So every time you go down 6 decibels, I'm going to cut the voltage in half. Now, why is this really important? Because if you bring the two concepts together, power and voltage, here's what happens. Let's say that I start off with 100 volts. And for a given load, I have 20 watts at 100 volts. Just making numbers up. It doesn't matter what it is. Well, if I go from 100 volts down to 50 volts, how many dB is that? I'm cutting the voltage in half. That's minus 6 dB. But think about this. If I go from 20 watts down 6 decibels, what's going to happen? Well, when I go from 20 watts to 10 watts, I've gone down minus 3 decibels. Now I have to go down 3 more because I'm only at 3. If I go down 3 more decibels, minus 3 subtract 3 is minus 6 decibels. So what happens to the power? Well, it goes from 10 watts minus 3 decibels would be 5 watts. So here's an important concept. Any time I go down 6 decibels or have a 6 decibel loss, I'm cutting the voltage in half. But what does that do to the power? It makes you have only 1/4 of the power left. Because 5 watts is only 1/4 of 20 in this example. All right, there you have it. Most important numbers for decibels is 6 and 3. Positive 3 means a doubling of the power. Positive 6 means a doubling of the voltage. Negative 3 means cutting the power in half. Negative 6 means cutting the voltage in half. I hope you got that. Here's some examples. See if you can understand these. The power to a speaker has increased from 100 watts to 200 watts. How many dB is this? Well, first, is it watts or volts? You need to know that. You need to know if it's watts or volts. Well, it's watts. So if I double the watts, how many dB would that be? That would be a positive 3 dB, or an increase of 3 dB. Now look at this next one. And our signal voltage is decreased by 50%. We don't even have to know the voltage, but we know that it went down to 1/2. Well, how many decibels is that? Well, that's a loss of 6 dB. I can say a loss of 6 dB, but if I was going to write it, that would be a negative 6 dB. The voltage is cut in half. Notice up here is power, and down there it was voltage. Okay, a transmitter decreases its power from 100. Oh, that's not decreasing. Oh yeah, it's decreasing. Decreasing from 100 watts to 500 watts. How many decibel decrease is this? Well, it's power. Half of the power would be a loss of 3 dB, And if you were writing, it would be a negative 3 dB, minus 3 dB. An AC voltage change from 12 to 24 volts. How many decibels would this be? Well, it's voltage. Doubling the voltage would be a positive 6 dB. Those are the kind of questions you're going to see. There's actually a lot more behind the math of finding decibels. For example, current converting from voltages or watts to decibels. We're not going to get into that. You don't have to do that on CT exam, but you need to know this basic information. What is the meaning of positive 3 and positive 6 decibels? What is the meaning of negative 3 and negative 6 decibels? You will have those. All right, let's move on to connectors. Let's talk about connectors. I thought this is a pretty interesting picture here. What do you think? Look at all the different connectors on this. Look at all those connectors. And look, this is some kind of universal converter box. And over here, you got all these other connectors over here. These probably are most of the connectors you would ever see in communications electronics, all kinds. But, except for this one, this gas pump thing. That's, I guess, it's supposed to be funny. But let's talk about the ones that just may appear on the CET exam. I'm hoping you've seen some of these before. For example, have we seen this before? Where have you seen that? Have you not seen that on the end of your O-scope probe? Well, on your own scope, you have something called a B&C. Quite often, the B&C is called a British Naval connector. In reality, it's not a British Naval connector, but it's a bayonet Neil Councilman. That's what the actual name of it is. So that's a B&C. That's the name of that connector. That's typically used as a radio frequency connector working in the megahertz range, maybe 100 megahertz, maybe even up to a gigahertz. But it's used for all kinds of communication equipment, mostly for test equipment, though. You almost always see it first doing some kind of tests when you work with it. Okay, this is a, what is this connector? Have you ever seen this before? The way that you make it is you strip this wire a certain way, and then you put the connector on it. You slide it on, and sometimes you crimp it back here. Here's one with a crimp on it. Well, what is this? This is an F connector. That's right. It's an F connector. F. If you don't know what it's called. It's very common for cable TV in your house and for internet connections with a cable modem. So this is an F connector. It's very common for cable TV. Next one. Well, what is this? What's this thing? Have you seen this before? Hopefully you have. I think you've had networking class. This is called an RJ connector. An RJ. There's different sizes of RJs. The one that they use for your computer is called an RJ45. It actually came from the phone company. For example, this one right here is a common phone plug, and this one up here would be an RJ45 internet connector. So what is this connector? It's an RJ. What is it used for? It's typically used for computer networking or for landline telephones. An RJ connector. All right, does anybody recognize this? What is this thing? Come on, gas and oil majors. Do you know what this thing is? Have you seen it before? Well, this is called a D connector. This is called a D connector. Why? Look at the shape of this. It's like a shape of a D laying on its side. This is the socket side here. This would be a DB9 socket. This would be a DB9 plug up here. A plug. Now, interesting point here. They call this a DB9, the one that I have circled here, but in reality it's a DE9 because a DB is the size of the shell, and this is actually an E-size shell. So hopefully you know that DB9s today are improperly called DB9s. They're really DE9s, but you just need to know it's a D connector. What is it used for? It's used for serial communications with industrial control equipment. So this is a serial communication port jack. Typically, on the DTE device, you'll find a male connector or a plug. On the DCE device, you will find a female connector or the sockets. All right, there you go. That's all you need to know for connectors. We've talked about decibels in communication. We've talked about connectors in communication. How about we talk about frequencies used in communications? Frequency. I got a kick out of this picture here because humans cannot hear 50,000 hertz, but dogs typically can. Dogs can hear way above the frequencies of human hearing. Now, what I'm concerned about, though, is for you, you need to be familiar with many of these different ranges. I am a little bit concerned because I teach the day classes, and I know that many of the students make it through their first year, and they have no idea what the frequencies of human voice are, or what the frequencies of AM broadcast stations are, or what the frequency of TV is, or what the frequency of FM radio is, or even what the frequency of their cell phone, or what the frequency of fiber optics are. If you don't know these, and you're an electronic technician, you better add this to your skill set. You need to know what are the frequencies of the range of frequencies of certain things that you encounter in electronics. It's only a neophyte who does not know these different frequencies. So make sure you learn them. I'll point out the ones that you should know. Okay, so you can refer back to this when we start moving on here. For example, what are audio frequencies? Would you be able to explain that to somebody in an interview? What is an audio frequency? Well, if you're thinking in your mind, audio frequencies are frequencies you can hear with the human ear, frequencies that humans can hear, those are audio frequencies. Audio frequencies, frequencies that humans can hear. What can you hear? You can hear voice, you can hear insects, you can hear music. Those are all probably in the audio frequency range. Well, what is the audio frequency range? Well, the audio frequency range is between 20 hertz up through the range 20 kilohertz. Those are the range of audio frequencies. What is the bandwidth? Well, the bandwidth is the upper frequency minus the lower frequency. In this case, 20 hertz is so much lower than 20 kilohertz, it's almost zero. You can say that the bandwidth that you subtracted 2 is approximately 20 kilohertz. Okay. Now, in reality, if you're older like me, you could never hear 20 kilohertz. The youngsters hear it. But I can only probably hear up to about 12 or 10 kilohertz. They might give you something like this right here, though. Look at this picture over here to the right. They might ask you, what frequencies are these? Well, if I look at this closely, it's a frequency response curve. You should recognize it as such from second quarter. Here are the lower frequencies. There's the lowest cutoff frequencies down around 50. Here is your upper cutoff frequency. It looks like it's around 20 kilohertz up here. So when you see a picture of this on the test, you're going to identify it as being audio frequencies. It's around 20 to 20 kilohertz there. You can see the frequencies down here. This, by the way, is called a logarithmic chart, because what you see here is you're moving in octaves. Every time you have a notch here, you're doubling it, like 50, 20 to 50, 50 to 100, 100 to 200, 4, 5, 1K, 2K. It's called a logarithmic chart. Now, I know this is a little bit out of order here, but what is the typical frequency used to test frequencies, audio frequency circuitry? Well, generally we'll pick a frequency right in the middle of this chart someplace. Well, there it is. Right in the middle of that chart, on that log chart, is 1K. So generally, the general frequency, approximate frequency of human voice and audio frequencies is around 1 kilohertz. That's in the center of the range of frequencies that we can hear. You need to know that. That's a typical test tone that we can use to check audio frequency circuits. Okay, speaking of audio frequencies, you need to know a little bit about a microphone. What is a microphone? Well, a microphone is a circuit that converts sound energy into electrical energy. What is a transducer? A transducer is a device that converts energy in one form to another. For example, a light bulb is a transducer, converts electrical energy into light and heat. A toaster is a transducer, electrical energy into heat. So a microphone is a transducer that converts sound to electrical energy. It's a special type of transducer. You guys that are in the industrial classes, they have transducers for sensors. For example, converting pressure into an electrical signal. That would be a type of transducer. I typically just call them sensors. It makes it a little bit easier to understand. Okay, what are the two popular types of microphones? Well, one of them is resistive, a resistive microphone. Another one, one type is a carbon microphone. Carbon, that's one type. Another type of microphone is capacitive. Now, an old word for capacitor is what? An old word for capacitor is condenser. That's an old word for capacitor. So sometimes you'll hear these microphones called condenser microphones. So carbon microphone and capacitive microphone. How do they work? Well, let's talk about this carbon microphone first. Here's a pictorial of it. Here's the heart of it right here. Inside of this metal shell is a bunch of carbon granules. And when the sound comes down and hits those carbon granules, the carbon granules compress and decompress or shake around. And that makes the resistance between these 2 points change. So a higher pressure sound wave makes lower resistance in there. A lower pressure sound wave makes more resistance in there. And all that does is vary the current in the loop. That's all that it does. So a carbon microphone works by varying its resistance. The sound waves shake the carbon, and the carbon changes its resistance. So a carbon microphone works like a resistor, a variable resistor. That's how it works. This is not the pictorial of a carbon microphone, a schematic carbon microphone. It's just telling you that it behaves like a variable resistor. Now, capacitive microphone, look at it right here. Capacitor is built with 2 plates. A capacitive microphone works like a variable capacitor, but how does it work? Well, here's one plate separated by an insulator, and here's another plate behind it. And so, what happens here is when I talk into the microphone, this condenser microphone, it makes this plate here move closer together or further apart from the other plate. And remember, that's how capacitance changes. So this one, a condenser or capacitive microphone, actually changes its capacitance according to the sound waves. So that one acts like a variable capacitor. You'll probably see one of these two on the test. Carbon microphone works like a variable resistor. It varies its resistance according to the sound that hits it. A capacitive microphone varies its capacitance according to the sound that hits it, and so it's a variable capacitor in design. Again, this is the schematic of a variable cap, not of a capacitive microphone. All right, moving on and talking a little bit more about frequencies. What is video? What are video frequencies? Well, video frequencies are the frequencies that we need to make pictures appear on your screen of your computer or on your TV set. Video frequencies, the frequencies that we need to make the intelligence of video. Like we said, audio frequencies, those are the frequencies that we need to make sound. Video frequencies are the frequencies we need to make something that we can see. Video, seeing it with your eyes. What is the range of video frequencies? Well, the range of video frequencies is between 0 and 4 or 0 and 6 megahertz. Some of them will even be up to about 10 megahertz. But on the test, they usually ask you about 0 to 4 or 0 to 6. So what would be the bandwidth of a video amp? Well, the upper frequency minus the lower frequency is going to be 4 to 6 megahertz. So sometimes the answer is 4 megahertz, not little m, capital M, megahertz, or the bandwidth of a video amp might be 6 megahertz. These are the intelligence frequencies that we need to make things that we can see on a screen. These are the intelligence frequencies for video amps. You will see video amps in televisions. You will see video amps in radar sets, because radar sets actually have a television screen associated with them. Now, if you look down here, here's the typical frequency response curve for a video amp. You see it goes from here, a very, very low frequency, around 0, up through around, this one's going up to about 20 megahertz or so. That's a pretty wide band amplifier. Video amps are said to be wideband because they really reach up into the higher frequencies of intelligence. Okay. Before we move on, let's go back here for a moment. These original frequencies. There are some frequencies that you should be familiar with. You should be familiar with these frequencies, UHF, VHF, and HF. These are very common carrier frequencies used for wireless radio. They're going to probably ask you a couple questions of them. That's what we're coming up to here. I wanted to make sure that you were aware of that before we moved on. So let's talk about cables and waveguides. Another name for a cable that is used to connect two communication devices together is transmission line. Transmission line is another name for a cable connecting two communication devices together. Boy, do you remember all this from 5th quarter? I hope so. I hope your teacher covered this in 5th quarter. Now, what are two very common cable types that are used as transmission lines? Well, the most popular, there's two really popular kinds. Although there's about 5 or 6 of them, the ones that you'll be tested on will be the coaxial cable and the twisted pair. In serial communication, you always run into the twisted pair. Coaxial cable is typically in RF, testing RF. For example, your BNC to alligator cable in your kit or your oscilloscope probe is a type of coaxial cable. Why are they called coaxial? The center conductor is in the middle. It's coaxially placed to the other conductor, which is the shield. Why is this called twisted pair? Because the wires are twisted together in pairs. You have UTP, unshielded twisted pair, and shielded twisted pair. There's two kinds, STP and UTP. Now, what is replacing twisted pair today in many communication systems? Well, twisted pair is kind of an old piece of transmission line. It's very, very old. It comes from the original telephone system. Fiber optics has been replacing twisted pair in many applications. Fiber optics replacing twisted pair. Now, the interesting thing about a transmission line is, first off, you all know that the three main parts of any communication system is the transmitter, the medium, sometimes called the link or the medium, and what else? The third part is the receiver. At least you know that. Hopefully you've learned that in your class. Okay, so you have the transmitter, where the communication originates, the link, how the communication gets to the next device, the device that receives it, called the receiver. Those are the three parts. Now, a transmission line is very interesting because we think that when a voltage appears here, it instantaneously appears here. In reality, the fastest the signal can get from here to there is a speed of 3 times 10 to the 8th meters per second, which is the speed of light. Here's an example. The sun is pretty far away from the earth. The sunlight that we see does not instantaneously happen on the sun. The sunlight that we see is actually 8 minutes old. Because it travels at 3 times 10 to the 8th, or 300 million meters per second, it takes a long time for those radio waves of light to get to the earth. So if the sun was to blow up right now, you wouldn't know for 8 minutes. Now, ideally, in this transmission line right here, this wire connecting this to here from there to there, we would like it to be instantaneous, or at the very least at the speed of light traveling down there. So when I put a signal in here, it takes time for the signal to get over there, a measurable amount of time. Sometimes we call that latency, sometimes we call that propagation delay. But in a cable, the wave always travels a little bit slower than the speed of light, or the speed of a radio wave in free space. Now, the comparison of how fast the wave travels in that line compared to free space is called the velocity factor. So, some cables have a very high velocity factor, which is very good, and those ones typically have a lot of air bubbles inside of them. The insulation is made out of air bubbles. Some of them have a pretty slow velocity factor. They run pretty slow compared to the speed of light or a radio wave in free space. Those ones are typically solid plastic for their insulator. But what causes the velocity factor to only be about 60 or 70% of the speed in free space, the wave in free space? Well, that is the insulation. The kind of insulation that they use. The insulation that's between the conductors in a wire that is used as a transmission line is called a dielectric. And you can see here, if I make a very foamy dielectric, a lot of air bubbles in there, or a lot of airspace or airspace Teflon, I have very, very high speed in the line. If I use solid plastic, like a lot of these over here, solid plastic, I have a very, very slow moving wave in comparison. So if my speed of light is 3 times 10 to the 8th meters per second, about 66% is about 2 times 10 to the 8th meters per second. So the important concept here is, when you use wires or a radio wave or even fiber optics, it takes time for the signal from the transmitter to get to the receiver. There's a delay there. It's called the propagation delay. How fast it gets there is called the velocity factor. The velocity factor in a line is much slower. It's slower by about 30%, 40 to 30%, which means it runs at about 60 or 70% of the speed in free space. So what causes that? The type of insulation, or in this case, it's called the dielectric. These are all examples of really old cables that I found, and you know, this is some really old stuff. Some of these are used for cables and communication systems, some are not. Now here's your historic bell wire down here, and here's your type twisted pair. So all these typically have a plastic, solid plastic insulator between them, and those would probably have a velocity factor of about 60%. Now, when I use a piece of cable as a connection between a transmitter and receiver, it's called a transmission line, but what kind of circuit does it behave like? Although there's no real inductor or capacitor in there, because of the construction of the cable, it behaves like a low-pass filter. I can tell it's a low-pass filter from second quarter because the inductor is in series with the output and the capacitance is in parallel with the output. That would be a type of low-pass filter. Why? Well, if I combine those two, you learned them like this. Here's a low-pass filter, the resistor going to common. Here's your input here on the left, and here's your output here on the right. The inductor is in series with the output. That's what we have here, inductor. And the capacitor, if you have a low-pass filter with a capacitor, you have a resistor in the top of the L network and a capacitor here. Now, if you combine those two together, here's your input and here's your output. If you combine a capacitor in parallel with an inductor in series, you get what you see over here. So every piece of wire that is used to get communication from one point to another behaves like a low-pass filter. Again, hopefully this was taught to you in your fifth quarter class. So the two wires separated by an insulator, think about that. That's like a capacitor. Capacitor is two conductors separated by an insulator, right? That's what creates the capacitance in the wire. And the length of the wire itself has magnetic field building up around it. That creates the inductance. So the representation of a cable connecting between two devices would be a low-pass filter. It looks like this. You have one device on the left. You have one device over here on the left, the transmitter. And over here at the receiver, you have the inductor in series with the receiver and the capacitor in parallel with the receiver. This right here is a low-pass filter. This is a low-pass filter. What causes the low-pass action? The inductance of the cable and the length of it and the capacitance between the two conductors, especially in twisted pair. All right, another concept about cables that you need to be familiar with. All transmission lines and cables, because it behaves like a circuit, in this case a low-pass filter, will have a rated impedance. And that rated impedance of the cable is very, very important. So, cables that are connecting two devices. Here's a device here, a transmitter, here's the receiver, and here's the transmission line. When the AC gets into the cable, it sees an impedance. When it enters that low-pass filter, there's an input and an output impedance when it leaves it. So every transmission line has an impedance. What does that mean? That is the number of ohms in reactance and resistance that cable sees, that signal sees when going into or leaving the cable. So a transmission line acts like a circuit. We have to treat it as such. That transmission line or twisted pair or coaxial cable will have an impedance. That impedance is very, very important. What is the impedance of that cable? It's what the AC signal sees when trying to get in or leaving the cable. Why is it very, very important? Well, you have to match the impedance of the cable to the device it's connected to. If it's connected to a receiver over here, that receiver will have an input impedance. That's the impedance of the load. The impedance coming out of this cable right here has to match the impedance of the load to get proper power transfer. Proper power transfer. Here's an example down here. I send a signal in from the transmitter. That signal travels down the line. You see it here, it's moving down the line. If the impedance of this receiver matches the impedance of the line, all the energy in the line will go into the receiver. If it does not match, what will happen is not all of the energy will go into the load or the receiver. And when that happens, that power has to go someplace. And it ends up bouncing off the end of the line and traveling back up the line. That's called the reflected or reverse signal. And that ends up combining with something that's coming back down the other direction. And it changes the shape of the wave. This is called corruption of the digital signal. So, why must the impedances match? If you have a mismatch, you will not have proper power transfer. It will cause reflections on the line. Typically, what ends up happening is you have a mismatch on both ends. The signal will just bounce around between the transmitter and receiver and cause standing waves. That's more than we need to talk about here. All you need to know is cables have a characteristic impedance. It's called the impedance of the line. The impedance of the cable has to match the impedance of the device it's connected to. If it does, it works properly. If it doesn't, you get reflections which can cause problems. So, in a communication circuit, you never mix cables with different impedances, and you always try to match the impedance of the device to the cable or to another cable. Here is a very, very confusing topic regarding transmission lines or cables used as transmission lines. Typically, your communications cable will have two wires, even if it's twisted pair or if it's a coax. So you have two wires from the transmitter end to the receiver end. Now, a good way to check this is you need to see if this cable is good, you need to measure the ohms from here to here. And you should have the cable disconnected on both ends. Now, what should this read between here and here if it's properly disconnected on both ends? I should read infinity. I should read infinity ohms. It should read an open. So, we confuse the impedance of the cable with the resistance of the cable. The impedance of the cable is what the AC signal sees. A DMM measures resistance. So you cannot measure the impedance of a cable with a DMM. You cannot measure it. The impedance of a cable cannot be measured with a DMM. Why? Impedance is what the AC signal sees coming from the transmitter or going to the receiver. A DMM measures DC resistance. So, listen to this. Let's say right here that my twisted pair is rated with an impedance of 100 ohms. That's a typical impedance of twisted pair. I hope you've learned that. So, some technicians think that if I measure with a DMM, an ohm meter between there and there, that what should I read? Well, they're thinking I should read 100 ohms. No. If it's open on both ends, I'm going to read infinity. Why? Because the DMM reads resistance. It does not read impedance. If I did measure there, and I read 100 ohms, that would be a faulty reading, even if it was a 100 ohm rated cable. Why? Because the DMM reads DC values, and if it's properly disconnected on both ends, it will read infinity. If I actually read 100 ohms there, there's probably a short or a partial short in the cable or on the connectors. So don't confuse the impedance of the cable with the DC ohms reading of the cable. What does it mean, number 12? If the cable is open at both ends, but with a DMM I read something near the rated impedance of the cable? that means I probably have a short in there someplace. So don't be fooled by that question. Hopefully you got enough background on that. If you have to, Google it or email me and I'll talk with you more about it if you so desire. All right, so important tips regarding transmission lines. You never mix or connect together cables of different rated impedances. The impedance of the cable should match the input impedance of the device it's connected to, whether it's a device or another cable. The reason is because you need to have the proper power transfer. If it's not the same impedance, you're going to get reflections that cause trouble in the line. The impedance of the cable is not measurable with a DMM. So don't think you're going to check a 50 ohm coaxial cable or a 75 ohm coaxial cable and find out that it's 75 or 50 ohms. No. If it's disconnected on both ends, it should read infinity. A good cable will always read infinity between the wires if it's disconnected at both ends, regardless of its impedance rating. Okay. Why are cables not typically used for frequencies above 1 gigahertz? And if we go into that chart, we'll see that 1 gigahertz is in the SHF range or the UHF range, up in that area. And that's a really high radio frequency. Those are really high frequencies. And cables actually act like a low-pass filter. So you're going to get too much attenuation. It will not let the signal pass through because cables behave like a low-pass filter. For those applications, if you're not using wireless, you might use something called a waveguide for frequencies that are up in the UHF or SHF range. Anything above VHF or UHF, you probably want to stay away from cables because they have too much attenuation or loss. Here's some pictures of waveguides here. Waveguides are just metal tubes that you shoot your wave in to one side from the transmitter. It's received at the other side of the receiver. You're guiding a radio wave through a waveguide. We typically use waveguides for very, very high frequencies, UHF, SHF, and frequencies above. Waveguides are very, very popular for satellite and high-power cell phone communication. And the reason is you want to stay away from coaxial cables and twisted pair, especially at those frequencies. Your cell phone works around 2, 4, or 5 gigahertz. Satellite communication, 20 or 30 gigahertz, very, very high frequencies. Oddly enough, a waveguide behaves like a high-pass filter, so it's very nice for really high frequencies. Now, why are waveguides typically not used in the HF or VHF range, where you would typically use cables? Well, here's why. Looking here, this is an actual waveguide. It's a very, very large waveguide. It's got to be 4 or 5 feet across right here. I think this waveguide was taken at the largest satellite dish in the world, Arecibo in Puerto Rico. I've been there. But the lower the frequency that you use with the waveguide, the bigger the waveguide has to be. This is probably a 300 megahertz waveguide, I bet. It looks pretty large. It's around 300 megahertz. It's really big. So why are waveguides not used below 1 gigahertz in the HF and VHF range? Well, it's because the waveguides become too large and too cumbersome. They call this the AB window here when you look at this rectangular side. The A side is the long side, and the B side is the short side. And the A dimension and the B dimension has a lot to do with the lower cutoff frequency. And the lower cutoff frequency is inversely related to the size. So, here's a question for you. Why do you typically not use coaxial or twisted pair above VHF? You have too much loss because they act like low-pass filters. Why do you typically not use waveguides below these frequencies? The waveguides are too big. All right, you ready to talk about some mean communication circuitry? Communication circuitry that you should be familiar with are oscillators. discrete amplifier circuits we've talked in the past, common collector, common emitter. And we'll talk about some op-amps here. There are circuits that are common in the basic landline telephone system and more. Let's talk about these. Okay, what is an oscillator? Does anybody know what an oscillator is? Did you study oscillators? Well, you possibly had it in third quarter. If not, you should have had it in fifth quarter. An oscillator is a circuit that generates a continuous, steady output AC frequency. Oscillators have no input except for the DC voltage applied. They are designed to generate a steady, solid frequency and peak-to-peak voltage. In communication circuits, oscillators are used to generate a carrier frequency. That's the wireless wave that goes across an antenna from one antenna to another. That's a carrier. So in communication circuits, we use oscillators to make a carrier frequency. Carrier frequencies are very, very stable. Now, how do I normally identify an LC oscillator? Well, L and C means an inductive or capacitive oscillator. Inductive, capacitive. These are the frequency determining components. And you'll recall that in a Class C amplifier, that the frequency of operation for an LC tuned circuit is equal to 1 over 2 pi square root LC. Remember that? 1 over 2 pi square root LC. Okay. Now, oscillators don't have an input. Here's a common emitter amplifier here. I have an input and an output. Input on the base, output off of the collector. And a common emitter amplifier can be used as an oscillator, but we have to take part of its output and feed it back to its input. The frequency determining components are this yellow block here. This is the LC circuit. This is a Hartley oscillator. I can tell because it has a split inductor, but you don't need to worry about that. All you need to know is there's a feedback loop for an oscillator. The output comes off of the collector, and the input goes into the base, but it's self-feeding. It feeds itself with its own signal. So there's no separate output over here, any input over here. As soon as I turn the circuit on, it starts generating a frequency that comes off of the circuit right here. Comes off here, this would be your output. The identifying feature that tells me this is an oscillator, not a standard common emitter amplifier, is in the feedback loop between the output and the input is a tank circuit, an LC circuit that determines the frequency of operation. That LC circuit could be here, it could be down here on the bottom in the feedback loop, or it could be over here. But these are the frequency determining components. So, what is the circuit identifying feature that all LC oscillators possess? Well, they're a common emitter amp. It has a feedback loop from output to input, and in that feedback loop you will have an LC circuit. That tells you it's an oscillator. Another kind of oscillator is a crystal oscillator. Crystal oscillator uses a quartz crystal. Here is the schematic diagram of a crystal, a quartz crystal. A block of quartz separated by two plates. Looks kind of similar to a cap, but it's not. What is a crystal? A crystal is a piece of quartz that behaves like an LC circuit. It'll generate a certain frequency. The frequency that it generates will be determined by the size and the cut of the crystal. Generally, the larger the crystal, the lower the frequency. Here are some examples of crystals here. You probably had one of these in your kit. More often than not, the frequency of the crystal is written right on the side of the crystal. These don't have the frequency written on them. But crystals are very, very precise. You know, this might say 5.1795 megahertz on it. Now, crystals can be the frequency determining component of an oscillator, or they can use by themselves and plugged in can generate different frequencies for a transmitter or to receive different frequencies in a receiver. But how does a crystal work? A crystal works by the piezoelectric effect. Here's how the piezoelectric effect works. If I mechanically twist this crystal, it will generate a voltage. When I release the twisting of the crystal, it'll pull voltage in or power in. So, well, that's a little bit confusing. Look at the diagram down here. If I pull it apart, it generates one polarity of charge. If I push it together, it generates another. We typically call this twisting, and this is greatly exaggerated here. Here's another example here. If I attach two probes to the opposite side of this quartz crystal and I hit it with a hammer, I could generate a little spike of electricity. This thing can light a light bulb, but that's probably not enough energy to do that. But the piezoelectric effect is when I apply pressure to a crystal, it will generate a spike of electricity. That's the concept behind it. Typically, we refer to it as twisting. Here's what ends up happening. When I apply a voltage to this terminal here on the crystal, I can make this crystal twist. When I release the voltage from that crystal, it'll twist back and release the voltage back into the circuit. So that's what we mean by the piezoelectric effect. It's typically experienced with quartz crystals. I think the question that you'll see will be something like, the effect that a quartz crystal utilizes to generate a frequency is the, and then you'll have to answer piezoelectric effect. It'll be something like that. All right. In communication circuits, it's very, very common to use the 10x setting of the probe when you're using the O-scope. If you look at your probe, there's a little switch on there. It says 10x, reference, and 1x. 1x is where you normally put the probe for most circuits. 10x is the setting you would use if you're using a communication circuit. What does the 10x setting have? What effect does it have on your reading? Well, when I set the probe to 10x, the 10x setting on the scope probe reduces the size of the scope image. And this is confusing. It's not multiplying the size of the image by 10. It's reducing it by a factor of 10. Well, why, McNeil, do they call it 10x then? Well, the reason why they call it 10x is because whatever you read on the scope, it's going to be 10 times that value. For example, I have my scope set to 10x. And I read on the scope, here to here, I read 1 volt peak to peak. If I'm set on 10x, I'm reading 1 volt peak to peak, but what is it really? Well, 10 times 1 will be 10 volts peak to peak. So the reading on the scope is always 10 times smaller. Don't let that one get you. So, to get the right reading when you use the 10x probe, I have to multiply the scope reading by 10 because it's 10 times smaller. Now, why do we even use the 10x setting? Well, here's why. On the 1x setting, the one-time setting, the scope can affect a very, very sensitive circuit. It's called the loading effects. For example, if I'm reading an oscillator's frequency, it's supposed to be oscillating at 1 megahertz. If I just put that probe on that oscillator, it might shift the frequency a little bit to 900 kilohertz or 1.1 megahertz. It won't read properly. By putting it on 10x, that's reducing the loading effects. It has less of an effect on the operation of the circuit. So that's why we like to use the 10x setting in communication circuits. It reduces the effects or loading effects that the scope has on the true reading of the circuit. Okay, what is the most common op-amp configuration that you'll run into? Well, the most common op-amp configuration you're going to run into is the inverting amp. I know that in your activity sheet it talks about inverting and non-inverting. I'm going to tell you now to save time. Focus in on the inverting amp. What does the inverting amplifier look like? It has an input resistor, Rn, connected to the inverting terminal, and I have a feedback resistor, Rf, that goes from the output to the input. That is your basic inverting amplifier. A takeoff of the basic inverting amplifier is this one down here. It's exactly the same thing. Rn to the inverting terminal, and then Rf over here from the output back in. And they'll sometimes have this in here. This is called a compensation resistor. Do not worry about it. So you'll either see this or you'll see that. They're both inverting amplifiers. How do I find the voltage gain of an inverting amplifier? I take the value of RF and I divide it by Rn, or Ri. So if this is 2K and this is 1K, 2 divided by 1 will give me a gain of 2. What does that mean? Whatever's coming in will be multiplied 2 to get on the output. Okay, so if I have a gain of 2 here with RF and Ri, and I have 10 volts coming in, 10 volts times my gain gives me my output. That would be 20 volts. Now, why are op-amps sometimes called DC amplifiers? Well, they can amplify DC voltages. Most other amplifiers cannot amplify DC voltage, but op-amps can. So that's why op-amps are sometimes called DC amps. You know, your basic common emitter and common collector cannot amplify DC. These special integrated circuits can. Okay. I know we're running a little bit long here today. I'm sorry about that, but there's a lot of material. All right. And then maybe you could split this up into two sittings if you want. I think we're getting close to the end if I'm not mistaken. All right. An inverting op-amp has an input of 0.5 volts, and that should say peak to peak on there, so why don't you fix that? 0.5 volts peak to peak. And it's riding on a DC bias of 2 volts. So essentially what you're putting into this amplifier is 2 volts DC, 2 volts DC. If this is 0 volts down here, 2 volts DC is up here. So you have a positive 2 volts DC, and riding on top of that 2 volt DC bias is 1 volt peak to peak, AC. I mean, a half a volt peak to peak AC riding in. Now you feed that in there into this op-amp. You're actually putting two signals in there, a 2 volt DC signal and a 0.5 volt peak to peak signal. They're two different things. They're riding together, but they're going to be treated as two different things in the op-amp. So, first, you got to calculate the gain. The RF over here is 2K. Your Ri is 1K. 2 divided by 1 gives me a voltage gain of 2. Here it is, right here. Figure the voltage gain. Your voltage gain is 2. Now, your formula for finding the V out is V out times V in. V in times my voltage gain gives me my output voltage. So over here, my input voltage times my voltage gain gives me my output voltage. So you have to do two calculations here. One is, what is the AC signal going to be? Well, I put 0.5 volts in, peak to peak. I multiply it by 2. My output would be 0.5 times 2, 1 volt peak to peak. So I have a 1 volt peak to peak signal coming out. That's the first part of this. The second part is the DC value. I'm putting in 2 volts, and what am my gain is 2 volts, so you would think I'm going to get 4 volts out. Well, you will. The problem is, this is an inverting amplifier. And an inverting amplifier inverts the voltage of the DC values. So really I'm getting 4 volts out, but it's going to be a negative 4 because I'm using the inverting terminal. So what am I getting out of this circuit? I'm going to be getting out of this circuit a negative 4 volts DC, and the signal that will be riding on it will be a 1 volt peak to peak volt, 1 volt peak to peak. Now you're going to ask yourself, well, if I flip the inversion of the DC, why don't I have a negative 1 volts peak to peak? Well, there's no polarity on the AC. That's why it's not a negative 1 volt peak to peak. It only inverts the voltage of the DC. So this would be my answer. I'm going to have a 1 volt peak to peak wave and a negative 4 volts DC coming out because I'm amplifying 2 signals at the same time. Very, very common with an op-amp. Okay, what happens to an op-amp's output if you exceed the input frequency's maximum limit? Well, on an op-amp, it acts like a low-pass filter. It works very, very good up to 1 frequency right here, and then it starts rolling off. You start losing gain. So what happens to an op-amp's output if the input frequency goes beyond its usable bandwidth? Well, here's its bandwidth right here, and here's the gain. If I go beyond the usable bandwidth, what's going to happen to my output? If this was an AC signal, I'm going to be losing peak-to-peak voltage. The output voltage would decrease if I go beyond the upper limit of the cutoff. Now, this is for op-amps, and it's for any amplifier circuit. Hopefully in third quarter you learned that the circuits are used for certain frequencies. They have frequency limits. And most amplifiers will behave like a low-pass filter. A lot of transistor amplifiers will act like a band-pass filter. Op-amp circuits act like a low-pass filter. So if I go beyond the upper cutoff frequency of an op-amp, if I go beyond its usable bandwidth, I'm going to have a decrease in power or voltage output. See, the gain drops from 94% down to 59%, down to an even lower value. All right, couple more things here, and then I think that we're finished. Kind of oddball stuff here. There is a question that you will see about the landline telephone system. It's also called the POTS system, the plain old telephone system, POTS. And in the plain old telephone system, where originally the twisted pair came from, here's the typical telephone wire that's in your house that has a red and a green wire. Okay, this is called the redundant pair, the yellow and the black. But the red and the green were the original colors of the original phone line that came to your house, the landline phone line. At the central office, or at the telephone company, CO central office, they have these big batteries there, and they're 48 volts. And the odd thing about this 48 volts is the positive is grounded. And so they feed a negative voltage to a red wire into your telephone at your house. This is your house, this is the telephone company, and this is the twisted pair between your house and the telephone company. So this wire here is called the red ring wire. It's red. Where does that come from? Well, it comes from this. On the old telephone plug for the operators, it was the ring on the plug. The tip is the one that's grounded right here. The tip wire is the green one. It's grounded. It's called the tip. Now, I'm not worried about what it's called or what the colors are, but what you need to know is that if your telephone's on the hook or you have your telephone unplugged, you're going to read at your house around the negative 48 from the red wire to ground. So in a telephone system that comes to your house, they're applying a negative 48 volts to your house to make that telephone work. Now, when you pick the phone off the hook and you're using it, there's a lot of resistance in that twisted pair. The voltage will drop to about a negative 12. But the CET question revolves around what voltage might you read at your home if you have your telephone on the hook and you were using a meter. Well, on your home, you might read up to about a negative 48. So negative 40 to negative 48 volts. All right, haha. One more slide, and then we can go into the fun stuff and do the practice quiz. Now, when it comes to noise in a wireless radio receiver, what is the most important stage? Well, in communications class, hopefully you've talked about noise. Noise is unwanted signals that get into your receiver that can change the shape of your wave. If you're dealing with data communication, noise Here's my data. It's a logic signal. Noise appears as small variations on the signal that change the shape of the wave. If I have too much noise in there, I can really mess up my wave. Okay, so noise is really important. It's unwanted changes in the wave shape. Now, when it comes to a wireless receiver, or any receiver actually, which stage is always the most important when it comes to noise? Well, in a wireless radio receiver, we have many amplifiers starting at the beginning, and they get amplified throughout. So, the very, very first stage, or the RF stage of a wireless receiver, or the first stage of any receiver, is always the most important when it comes to noise, because if I get electrical noise in the first stage, what's going to happen as it passes through these stages? Oh, even if it's a really, really tiny signal right here of noise, a really tiny amount of noise, as it passes through, it's going to be amplified higher and higher and higher. And I'm going to get static and buzzing and nastiness out of the speaker or the receiver because it's amplified through all the blocks in the block diagram. So the most important stage when it comes to a receiver is always the first stage. But it's important for you to know what stage is the first stage. It's the RF stage in a wireless receiver. Whew, that was a lot of stuff, wasn't it? That was a lot of stuff. Now, I am going to send you an email, and hopefully you've got the email before you watch this video. I'm going to tell you that it's about 2 hours long, and you're going to want to split it up into two separate hours. It's going to be difficult to watch the whole thing. If you watch the whole thing, you are a super student. That's okay with me. But anybody that can hear me talking for 2 hours straight, that's got to be punishment, and I know that. It's the trouble with some of these Collaborate videos. Sometimes they're just too long. Well, this is probably one of the most complicated things that we've talked about this quarter, so you might have to review it a couple of times, take good notes. Well, let's go ahead and take the practice quiz. All right. The item shown below is a, boy, that seems like an hour ago we talked about it, and it was. But what is this thing? What is this thing? What do you recognize it as? Well, what is that? Is that a British Naval connector? Is that a UHF? Is that an F connector? Well, let me mention something here. Which one of these did we talk about? Did we talk about the N connector? No. Did we talk about the UHF connector? No. We said the B and C is used for UHF. Did we talk about the PL259? No. So there's only two choices here for you. So use the process of elimination to help you get the right answer. You cannot spend too much time on it. Well, what is this? It's a B and C connector. Okay. Now, look at these. I'm going to show you how to use processes of elimination here. First of all, before I even read this question, did we talk about 1 dB? No. Did we talk about 2 dB? No. What were the two that we talked about, the 3 and the 6? Now, decreasing the voltage by 50% is going to be what number? Well, this is tricky because we said that a decrease was a negative number, but the word decrease in here automatically indicates it's going to be a negative number no matter what number I use. The next thing is, are we talking about voltage or power? Well, it's voltage. So having the voltage, you're taking the voltage and dividing it by 2, which is 50%, that will be a 6 decibel decrease. So my answer for that one is 6 dB. Okay? What frequency is most commonly used to troubleshoot audio? Well, we know audio frequencies are in what range? The 20 hertz to 20 kilohertz range. Which one of these are in the 20 to 20 kilohertz range? Oh, look at these tricky questions. 0.1 kilohertz, 1,000 kilohertz, 1 hertz, or 1 kilohertz? Well, we said right in the middle of the audio range is around 1 kilohertz. Now, this is in the audio range, but it's very, very low. Probably this is a subwoofer frequency. What is that? That's really 100 hertz. Look at this one. This is a distractor. That looks good, but it's not. If you're not careful, you won't see the K in there. So that's not 1,000 hertz. That's 1 megahertz there. 1,000 kilohertz is 1 megahertz. The only good answer here is 1 kilohertz. All right, look at this one. The velocity factor. The velocity factor of the transmission line is, well, first of all, velocity factor, use process of elimination here, is not equal to the termination impedance. Velocity factor is in meters per second, and the impedance is in ohms. How can you compare the two? The velocity factor is not determined by the length of the line. That's a common misconception. The length of the line has nothing to do with how fast the wave is traveling in it. Yeah, the propagation delay will be longer because it takes longer to get to the end of the line because it's a longer line, but it's still traveling at the same speed within. The velocity factor is increased by the distributed capacitance. No. The capacitance is in there. All that does is create a low-pass filter. What does affect the velocity factor? Well, the dielectric does. But what is the velocity factor? It's the speed of the wave compared to free space. So the only good answer here would be this D. Okay. The video bandwidth of the standard test definition analog TV or radar might be. Now let's think back. What was the band of frequencies usually associated with video? These are tricky. Here's why. 88 megahertz is an FM signal, FM carrier. That's not going to work. 24 megahertz. No, I have no idea where these came from. These are radio frequency carriers here. The only good answer here is 4 to 6 megahertz. That's the video bandwidth or video frequencies of video. All right, a carbon microphone behaves much like a what? Carbon varies the resistance in it when the sound hits it. Well, carbon microphones behave like a variable resistor. That's your answer for that one. These are very similar to what you're going to see on the test. Oh no. Here's that circuit, the one I was warning you about. Okay. First of all, look at the circuit below. Is it going to be an inverting or non-inverting amp? Well, the one that we talked about was the inverting. How can I tell? The input is going into the inverting terminal. What are the two resistors here that determine the gain? The feedback and the input resistor. So 2 divided by 1 gives me the voltage gain. The voltage gain, AV, is going to be equal to 2. 2 divided by 1. My V out of the amplifier is equal to the V in times the voltage gain. Now look at these answers. All these answers have 1 volt sine wave. So, you got to choose. Look, there's only 4 answers, and all 4 answers have the 1 volt sine wave. So do I even need to deal with this half of a volt? Well, I know that a half of a volt times 2 gives me 1 volt, but we know that. It's already given. The only thing we have to worry about are these DC voltages. So you don't even have to deal with the AC on this one. Okay, how many volts DC is coming in? 2 volts are coming in. That's the DC bias. So I put 2 volts here coming in, DC. So right here, a positive 2 volts, DC, times my voltage gain, 2. What does that equal? Well, that equals 4. Now, look at your answers. Is there a 4-volt DC level listed there somewhere? Yeah, it's in D. Right there. There's no other 4s here. 1, -1, -2, -4. The only possible answer would be this D. Why is it inverted to a -4? Well, you're using the inverting terminal. So I put a +2 in here. I'm going to get 4 out because of the voltage gain, but because I'm using the inverting terminal, it will be a -4. This one's a little bit easy to figure out by process of elimination. You should use process of elimination when you solve these more difficult ones. And let me tell you this too. When you take the CET exam, you will have a time limit. I would recommend that you go through and do all the easy ones first and then come back and work on the harder ones. Don't spend 5 or 10 minutes trying to figure something out. Pass it up and come back. You'll be able to bookmark and come back. So what was my answer for this one? B. All right, hey, what is this circuit below? Well, it's a common emitter amplifier. I can tell. It has your input on the base and the output off the collector. But look, it has a feedback loop on it coming from the output to the input. And what's in that feedback loop? Look, an LC tuned circuit. Now remember, we mentioned to you that tuned circuit might be over here in the feedback loop. It might be down here, so you have to watch. So what probably is this circuit? Most likely it's an oscillator because it has an LC circuit in its feedback loop. Okay, guess what? That was a long, hard road full of potholes. So I know that was difficult. That's one of the most difficult collaborate that you're going to have to deal with. There's a lot of good information in there. I probably should have split it up into 2, but we only have 10 weeks to prepare you. So spend a lot of time on this, digesting it. I'm going to say about 10% of the test revolves around these topics that we talked about here. So there will be at least 10, maybe 12 questions out of 100 that deal with communication circuits. If you get everything else right and don't get any communication topics correct, you can still pass this test. But try to get the easier ones of the ones that we've talked about. Now, I'll watch out for the releasing of the material on the Blackboard site. I'll put the test up there later this week. And make sure that you do the test if you're interested also. If you are not interested in taking the CET exam, I need you to actually let me know with an email. So please, let me know with an email. And then we can possibly work it out that you don't even have to watch any more of these Collaborate videos. I don't want to waste your time. If you've taken 6 quizzes and you've passed them, you've done okay, I can let you go. If you want to get ready for the CET, then continue on with me and I'll get you ready. I'm pretty sure we can get you to pass. By the way, some of you have been asking me, when are we going to have the CET exam? It'll be during the evening in the end of the quarter, and we'll have to get with you guys to find out what evening you can be here. I'll talk. I think you have Mr. Gamoose. I'll talk with him and see what's going on there. Maybe we could use one of those nights. I don't know. But let's go ahead and call it quits for today. And I guess I will talk to you guys next week. Okay. That's it for today, tonight, or this morning. And that's it.